Hi, everyone. I'm happy to kind of break the ice for this conference today. I'm Karel Crombecq from Briganti. I'm the lead programmer for a tool called Dungeon Alchemist. So, just a quick question. Who in this room has heard of Dungeon Alchemist before? Right, quite a few. Who has actually used it? Well, okay, thank you for that. So, what is Dungeon Alchemist? When the video starts loading, for those who don't know Dungeon Alchemist is a procedural. Wait. All right, there we are. Dungeon Alchemist is a procedural map-making tool for role-playing games, and I'm talking about tabletop role-playing games. So the idea is, as a dungeon master, you're going to have to make maps to put your tokens on and do your encounters. And Dungeon Alchemist is a procedural system that allows you to really efficiently, in like literally a few minutes, you can see it happen here, build really beautiful maps that you can use. You can print them afterwards, play in real life, or you can export them to a different tool like Foundry or Roll20 and then use it there. So just for the record, Dungeon Alchemist does not use any LLMs at all. Everything is like old school procedural generation. Just to get that out of here, because we get this question a lot nowadays, like, are you generating images or content or whatever? We don't. So what am I going to talk about today? When we did the initial Kickstarter for Dungeon Alchemist in 2021, the initial idea was basically to generate the furniture or interior of a room. So you would say, like, I want a castle bedroom, and we generate everything for you, like walls, floors, lights, all that kind of stuff. But as we developed, we started adding more and more procedural systems to the game, to the app, up until the point where we have a full stack of procedural algorithms that go all the way from terrain generation up to the roof of the building. And I'm going to go over them in this talk. I'm going to go pretty fast and I won't go too deep because it's only like 20 minutes and there's a lot to cover, but I'll do my best. Now, before we continue, one more caveat. I know this is a very kind of Houdini-oriented conference. So just to explain the stack we're developing in, Dungeon Alchemist was made in Unity. It's written in C#. We don't use Houdini at all. All the procedural systems were written from scratch in C#, mostly by me, over the course of 5 years. So just that you know that this is what we're talking about here. With that said, let's dive right into it. First step, terrain generation. So terrain generation in Dungeon Alchemist works like this. When you want to build a new map, you basically say, I want this map size, maybe 20 by 15 tiles or something, and you pick an elevation type, for example, mountains, ravine, hills, something like that. And then we generate a terrain that looks like this, including like an optional water feature, objects that are spawned on a terrain in a certain shape. And how we do this is the first thing I'm going to explain here. So, the first step in this whole process of like going from floor, like terrain all the way up to roofs, is generating the basic terrain. Now, probably if you're somewhat familiar with procedural, the first thing you say when you see this is like purling noise or something like that. That's like probably what immediately comes to mind, and you're absolutely right. But it's not that simple. Because we have a lot of like pretty complicated terrain types that we want to support. We built our own noise graph editor in Unity. So for that, we use 2 libraries. Whenever we use a library that's not written by ourselves, I'm going to mention it in the slides so that if you're interested in checking it out, you can take a photo and you know it. So the first one is libnoise. It's a very well-known noise library that generates coherent noise. So that means that it's kind of, you can extend it in any direction and it will not cut off harshly or something like that. It has a lot of like basic noise maps like Perlin, simplex noise, that kind of stuff. And then we have Xnode, which is another open source library that allows you to make node editors in Unity. And I kind of smashed these together to build this kind of graph editor system where you basically add different nodes, you create different noises, you can kind of drag them together and you get a final height map, and everything is kind of updated live in preview, so it's very convenient. And that way we can kind of efficiently design different kinds of height maps, basically, for the terrain. But what's even cooler is that this also really works in real time. So if you run Dungeon Alchemist, and you have a terrain, and you change a variable in like the different window where the node graph is, and you click change terrain, it will immediately kind of update the terrain in 3D, so you have like a real-time preview of what you're changing, which is a very convenient way of kind of iterating upon the kind of landscape you're trying to produce. So here I'm changing the octaves of the noise, and you immediately kind of see the difference in octaves of the resulting terrain. So that's the first step, right? We generate a height map for the terrain using this noise graph editor thing we made. Now on to texturing it, because that's a second part of it, of course. Once we have kind of a mesh generated based on this height map, we texture it using Microsplat. Microsplat is a paid plugin for Unity. It's a very powerful kind of drop-in replacement for the terrain tool of Unity that's kind of shitty. But it does a lot of stuff. It does a lot of stuff like even like erosion simulation and things like that. But we don't use any of that. We basically use it only for texture blending. So the idea is that you create a texture atlas from a bunch of textures, grass, sand, stuff like that. And then you determine kind of slopes for these different textures. Like some things should only spawn on very steep terrain, some things spawn on low elevations, some things should spawn kind of randomly all over the place. And then it blends them together into this kind of terrain. So in this example, we configured the rocks to only summon, to only appear at slopey terrain, and this like under sandy thing only to appear at lower elevations. So now we have a terrain, we have a height map, there's a mesh on top of it, it's textured. An additional feature we also add is that you can kind of override the default texture that is applied by Microsplat. So you can kind of paint on top of the terrain and apply your own texture on top of it, and it blends nicely together as well. So if you paint like grass and then you paint rock, it kind of blends rock and grass together into this kind of seamless thing where there's some grass popping through. So it's like pretty cool. That's also a Microsplat feature, so we didn't implement that part ourselves. With that done, next up is adding a water feature. So the first thing we realized was if we integrate a water feature in the terrain noise map, you're very limited, because you can have like a hill with a river and maybe a mountain with a lake or something, but if you want to have every possible combination of like elevation type with water type, you're going to have to make a lot of noise graphs. So instead we decided to use the noise graph editor to make separate height maps for the water, and then we blend them together. We kind of using a system where we prioritize where the water map kind of changes from the 0 axis. And that way you get something like this, where this is the original terrain, and we blend in a river on top of it, and you get this kind of result. And this allows us to make a lot of really kind of varying environments. You have like a desert canyon, a meadow river, a cave lake, jungle island, stuff like that. And it's all just a matter of combining two noise graphs that we made in our editor, smashing them together and texturing them. So the third and final step of the terrain generation would be adding some objects on top of it. And because we really like reusing stuff we already made, once again, we kind of used the noise graph editor for this time with a slightly different purpose. Instead of generating a height map from the output of the noise graph editor, we use it as kind of a density distribution graph. So basically, it will say like, all right, we generate some noise, and it says, this is how many objects of this type per square meter there should be spawning in this area. And we do this for what we call object family. So we have, let's say, a set of trees, a set of rocks, a set of grasses, and for every biome in Dungeon Alchemist, like this is like a forest biome, we define a distribution graph for each kind of object family. And if you see it spawning one by one, then it looks kind of like this, where there's like trees spawning first, then there's the undergrowth spawning, and then there's some rock spawning, and they're kind of clumped together because we made the noise graph like that for them to be clumped, because it makes sense for rocks. And then, so now we have a bit of a terrain, right? And that's step number one to getting to this point, where we get this building. We have a background, we have a terrain, now we want to generate buildings on top of this terrain. And And how do we go about doing that? So just to recap, how does Dungeon Alchemist work? You choose a room type. For example, you say, I want a castle bedroom. You draw a shape. This shape can contain curves and funky shapes and stuff like that, and diagonals. This is just a simple square example. And then it generates everything for you. It places doors, places columns, objects, lights, windows, all that kind of stuff. And it will do this in a specific order. It will generate first walls, then it will generate doors, then windows, then lights, and then kind of the furniture in the room. And I'm going to go over each one step by step. But all of these steps kind of use the same basic premise. How does Dungeon Alchemist know what a castle bedroom looks like? That's like a big question, right? For that, we developed a system that everything is based on. The idea is that we eat our own dog food. We first made a level editor that does not do procedural generation. And we design, or our art director designs, let's say this is a mansion living room, about 9 mansion living rooms in Dungeon Alchemist, saves them in a specific example file. And this example file, we run an analysis program on. And this program kind of tries to deduce how a mansion living room looks like. So it will look for relationships between objects. It will look for relationships between doors and walls and objects and all this kind of stuff. It will basically try to figure out as much information from the examples as possible. And one really important thing it tries to figure out is where are there patterns in this example. And with patterns, I mean objects that repeat on a regular basis. In this example, you see, like, for example, the lights are kind of a clear pattern. The windows are a clear pattern, but there's a lot more of them. If I overlay the pattern detection system on top of like an example, for example, here you see this is a castle bedroom example. You see that it detects like tons of different patterns. Lights are patterns. There's 2 shields right next to the bed, and it will store all this data. And this is not happening at runtime, right? This is happening when we are designing the example, and the analysis file is pushed in our build, so it's readily available to be loaded when you request a castle bedroom. It doesn't read the example file anymore at runtime. It just reads the analysis, and that's all it needs to kind of generate a bedroom. But that's not entirely true, but we'll get to that later. There's another step we have introduced. But for now, this is the basic idea. We have an example, we analyze the example, we have an analysis file, and we use this file to generate the rest of the room. First step is walls. Well, that seems like an easy one, right? You draw a shape, maybe a funky shape like this one, and you just put walls on the edges of the shape. Sounds like an easy part, but like you will notice with everything that's coming, there's always a caveat in this. And the caveat here is that we realized pretty early on that, let's say you have a wall type and you have a window type, and we want every window to fit into every wall. So either we need to find a way to, like, our artists, they have to make like a different wall version with a cutout for the window for each different window type, or we need to do this procedurally. We have curved walls, like you can see here. So do we pre-make curved versions of the walls? Obviously, this was never going to work. So we built this mesh manipulation pipeline that works at runtime. And it takes a basic mesh, and then it goes through a couple of steps to finally result in the final mesh that is being seen on the screen. So this is how it works. Let's say we have an initial mesh here on the left. This is just a simple like castle, crenellated castle wall. One thing that we quickly realized was that people don't always want the same interior wall as exterior wall. So maybe you would want bricks on the outside, but wallpaper on the inside. So we need a way to cut the wall in half and to be able to kind of glue another wall on the other side. So that's the first step. We cut the wall in half through runtime mesh manipulation, basically. Then let's say you want a curve in the wall. We curve this wall, and this is all just kind of on the vertex normal level. We just manipulate this with custom algorithms we wrote. And now let's say you want to put a window in this wall. Then we have to do a cutout of this window, and this is done with Boolean mesh manipulation. The way we do this efficiently is by approximating the window with boxes. So on the top you see the window, and then you see kind of the orange shapes. These are boxes that are used, and these are the ones that are being used to cut out a shape out of the wall mesh. As you can see, it's not like a perfect match with the window, but it doesn't matter because the window border kind of covers the shitty cutout. So it looks really beautiful when you see the final result. There you have a curved wall with a window that you can actually look through, and it's all just automatically done and based on this single wall mesh that someone made. We also reuse this, we cache all this data because typically when you're making a map, you're often reusing the same windows and wall types because you're making like a castle or a building or something. So we can kind of reuse a lot of this generated mesh data over and over again whenever a new window of that type is requested in the same wall, for example. So that's walls. Now we have walls, great. Let's do doors. Let's do doors next. Again, seems pretty easy. Put a door there and we're done. Well, it's not. The main challenge with doors is that you need to get a kind of logical building. We're not just generating a single room, right? We're generating a building. So what does this mean? You need to be able to get from every building to the terrain outside. So there needs to be a path going from every building outside. So we build a graph of kind of all connected rooms. And then we make sure that when you add a new room to it, that it makes sure that, for example, let's say you put a room in front of the one door that leads outside. Then we make sure we generate a new door that leads outside so that you can actually still get in the building. We also try to place the doors in a way that makes logical sense in terms of like how buildings are structured. Like doors prefer to be connected to hallways instead of to other, like a bedroom door would not be connected to another bedroom. As you can see here, like the doors are all placed facing the Great Hall in the middle, which is the logical way to do it. We could also place the door randomly in the wall on the top there, but we didn't. Then a third thing we take into account is also we try to place the doors as non-intrusive as possible, which means that we try to find a place where it doesn't have to delete any objects in adjacent rooms. Like we could have spawned the door behind the fireplace, but that wouldn't have worked. So then we would have had to delete the fireplace and we would have ruined a previously generated room. So that's not ideal. So we try to fit a place where we have to delete as little objects as possible to make it work. So that's doors. We have walls, we have doors. Now we have windows. Windows actually, and that's why I mentioned the pattern system, they rely very heavily on the pattern system. So we kind of realized, like if you look around here, windows are often quite systematic and patterned. So we look for patterns that match the shape that is being generated here. Like you can see, people can make some really funky shapes, so it's not always easy. And there's already a door there, there's adjacent rooms and stuff like that. But we try to find a pattern that matches, we stretch it, we shrink it, we kind of try to make it fit. And then we pick all the patterns that we find kind of good enough and randomly select one to get some like randomness in there. And that's the window setup you're gonna get. So that's a relatively easy part of it. Lights are generated the same way. They're also often very patterned, so we look for a pattern per room and we kind of generate this pattern again and place the torches against the walls. Some things we take into account, both for the windows and for the light sources, is kind of the orientation towards the door. This is actually a very good example of a room. I'm going to actually show a chapel that looks a lot like this later in the talk, because everything is oriented towards a specific direction, right? The lights, the windows, they're all kind of, there's a reason why there's, like, everything's aimed towards this. And we'll get to that when we go to the furniture step, which is coming up next. So this is the big one, right? This is where we started, and this is the first thing we implemented. So we have these examples, and we want to generate rooms based on top of these examples. Now, after messing around for a while, we realized that the analysis step just wasn't good enough to generate high-quality rooms. And the reason is this. Here we have a castle bedroom example again. The thing is, every bedroom in the example has a bed. Every bedroom has a closet. How does the system know that a bed is like a higher priority object than the closet? It doesn't. It can't really deduce this because there's closets and beds everywhere. But if you draw a really small bedroom, you definitely want the bed in there, and the closet is optional. So we introduced a different kind of post-processing step that we manually go in, and we can change, it's a layer editor we call it, we can change the priority of object spawning by dragging some objects in a different layer and kind of making the layer different. So this is kind of what it looks like. There's a lot of stuff in there because this is like a backend tool, so nobody has to really look at it a lot. But the main thing to note here is that the second column contains beds, and we drag them in front of the windows. So for this example, we said we consider beds even more important than windows. If you have to choose between beds and windows, please spawn a bed in a bedroom. And that's important because if you spawn windows first, and then in a very small room, and then you have to place a bed, the system doesn't allow you to block windows or doors and stuff like that. So it might happen that there's just no room to place a proper bed. So in this case, we overrode the default spawn behavior, and we said all right, we're doing beds first, then we're doing windows, then we're doing all the rest of the objects. So this allows us to also override the kind of tweak the spawn behavior of certain objects manually. For example, we could say this object is only allowed to spawn exactly in the center of a room, and if that's not possible, we're not doing it. This is very useful for statues in parks and stuff like that, which are typically you want to have perfectly centered and not kind of slightly off center, which looks off. So how does the object generation work step by step? Here we have kind of a half-generated kitchen. Let's say the algorithm decides based on the analysis that there's definitely a closet needed in this kitchen. It's large enough to fit a closet. Closet is next up in the priority queue of objects that need to be spawned. What it does first is it first generates basically all viable spawn locations for closets, and then it culls them based on some basic standard information like not in front of windows, not in front of doors. Those are easy to check and they're fast and efficient. After that, there's a bunch of closets remaining, and then it checks for collisions and stuff like that. So it kind of deletes all the closets that collide with other objects. We also take into account the fact that you need to be able to reach every part of the room from the door. So we don't allow a closet to kind of block off a part of the room that you can't get there anymore. And eventually, we have a bunch of closet position candidates left, and we rank them according to a whole bunch of criteria. Criteria like symmetry, how closely does this position resemble the position in the example file? Is it close to the door? Was it close to the door in the example? Is it close to other objects that are already spawned? Does this object typically spawn next to a table? Then we try to spawn it there and give it a higher priority. And then we finally settle on a closet over there right now. And then the step repeats until the algorithm kind of reaches the average amount of objects that are in the example file. So that's what it tries to do. It likes to generate the same amount of density. One other thing to note is this one here. Objects also kind of leave behind a metadata trace where they say this is where I am, and you can use this information if you really wanna. And this is the chapel I mentioned earlier. The altar is obviously the big, most important part of a chapel. So it's generated first. In the layer editor, we dragged it to the front. And then afterwards, everyone else knows, all right, the most important part is over there, so we're gonna orient ourselves towards that. So you're never gonna see a chapel generated with benches looking in the wrong direction. Also the windows, the lights, everything is kind of centered around the altar piece, and it's always like that. So with that being said, I only have about 5 minutes left, so we're getting there. We now have a fully furnished room, we have doors, we have walls, and now we get to the roofs. This is kind of a sneak preview. This is not in Dungeon Alchemist at the moment yet. It's coming up in our next update, which is being released in a few months. We're right now in early access, by the way, so you can already purchase this on Steam, but we're still actively updating it. So roofs and also second story buildings, or multi-story buildings, are something that are coming in the next update, but are not yet released. So here's a sneak preview of how that works. Now, one of the realizations we had early on when we were figuring out roofs is that a roof does not take on the same shape as a building or as a room. The thing is that you can see a roof as the intersection between two layers of rooms. And this means that you can create much more funky looking shapes in roofs than you could make in Dungeon Alchemist in rooms. This is like an example of a weird two-story building I just made up with all curves and diagonals and stuff like that. And these are the roof areas that where a roof should or should not spawn. As you can see, these are like pretty annoying shapes. And this means that we need to go back to all the mesh manipulation stuff to be able to fit whatever we have in terms of roof models to these weird shapes. So there's a lot of like cutting of models in parts to fit these really small things and stuff like that. I'm not going to be able to get into that in too much detail. Let's just say there's a lot of mesh manipulation going on here to make this work. But the biggest challenge, and probably one of the biggest ones I faced in the entire development of Dungeon Alchemist, was actually generating a slanted roof. And I feel like this is probably something, as far as I know, that's never really been done before. In The Sims, you're supposed to place roofs manually. An app like TinyGlade generates like circular roofs and rectangular roofs, but you have to kind of combine them together yourself to make a beautiful roof. We wanted to be able to, for any weird shape people come up with, we wanted to be able to generate a plausible 3D kind of slanted roof. We tried a lot of like algorithms that we developed ourselves, but that didn't really amount to anything. Every time we did that, we turned out that like some kind of weird shape we could come up with didn't really result in a beautiful roof. So at some point, I discovered on the internet an algorithm called the straight skeleton, which is not a very well-known algorithm, I think, in the games industry, but it's kind of an academic algorithm. There's like almost nothing to be found on it except for academic papers. There's 2 open source implementations that I found. They're both shitty, and they don't do what I want them to do. There's a paid version. I tried that one as well. That also doesn't do what I wanted to do. And it's a very, let's say, I'm going to skip over 3 months of absolutely agonizing pain to implement this algorithm. Because it's very numerically unstable. It's really hard to get it to work for every corner case. The good news is that I'm so frustrated with it that I decided to open source my implementation of the algorithm after the update is released, so in a couple of months. So other people who want to be able to generate roofs for these kind of shapes will be able to find my implementation on GitHub. It's Unity-based, so it's going to be C#, but if you're working in Unity, you can use it. So how does a straight skeleton work? I'm going to go over this pretty quickly. It's a very simple idea. The basic idea is that you have a polygon shape of a roof, and you shrink it kind of like Photoshop, the shrink filter. And you shrink it, and whenever an edge shrinks to 0 length, you put a point there, and you connect this point to the original edge points. And this results in this kind of shape, which can be seen as kind of the skeleton of a roof, right? That's why it's called straight skeleton. It was originally not developed for roofs, but they kind of discovered that it generates pretty well-looking roof shapes. They're not all like architecturally sound, obviously, but they look at least plausible. But that's only part 1, right? Now we have a shape, we can generate a mesh on top of it, but we also need to have proper roof tiles, and for that, we have this little problem where if you just do basic UV mapping, you get like squished UVs at these corners where there's curves. So that doesn't work. So instead, we took a different approach. What we did was, imagine if you're like spanning ropes horizontally across this straight skeleton, all the way to the top. These are like the purple, pink shapes here. And then you basically place tiles between the ropes, one by one. So it's a mesh generation process, like every tile is generated individually. We do some UV randomization, like offsetting, and then we kind of rotate and tilt them a little bit and scale them a little bit randomly so that you get these kind of really kind of artisanal looking roofs that I think are quite beautiful. And that's it, I guess. I went over the last part pretty quickly. I have like 0 seconds left, so here we are. Thank you very much. We have the whole stack covered. And if you want to talk about this stuff or have questions about specific algorithms or anything, don't hesitate to get in touch. I love to talk about this stuff. Thank you very much. Oh, there's time for questions. Oh, yeah, because we were messing about with the...
Okay. We are ready for some questions.
Hello. So you mentioned you have a analyzer for the room. So you build a room and then you analyze it using a tool.
Yeah.
Is that neural network based? Because it
No,
sounds.
it's a really... We started from the basic... that's what we tried at first.
Yeah.
We tried machine learning approaches and stuff, but it didn't amount to anything because you need way too much data. Like 9 examples don't cut it. So what we did was we started from how would you decorate a room? Basically, like if you're moving house and you need to decorate your bedroom, how do you do it? And then we built the analysis on top of that kind of information, like how would you do it? And we try to track all this information and reuse it later.
Basically, the same question about analyzes. Can you get more information about how do you analyze this thing? Like usually you will do like machine learning is like most obvious approach, but how do you do that?
How we do the analysis?
Yeah. Analysis, like feature extraction.
It's super brute force. We take every object in the example, and then we look at every wall, every other object nearby, and we kind of look if there's an object nearby. We track it, we track the distance, we track how far from a wall it spawns, and then we kind of mash all this information together, kind of summarize it and say like, all right, this object is always against the wall, so we're only going to spawn it against the wall. This object is always next to a table, so we're only going to spawn it against the table at this kind of difference average, and then there's some randomization on top of it as well. But it's mostly like just kind of trying to figure out every relationship that we could figure out, tracking it, saving it, and then using some of it at runtime.
I noticed that all your example rooms are square, but then the Dungeon Alchemist itself seems to support very irregular shaped rooms.
Yeah.
So surely you can't learn from square rooms how. Sorry, over here.
Oh yeah, sure. There you are.
Surely you can't learn from square rooms how to deal with all those sort of weirder cases.
Yeah, so the reason why there's mostly square rooms is honestly out of laziness. We only added curved walls in our last update, and I've been reusing videos we recorded earlier for different situations. But as you can see, there's this is a curved room, for example. The chapel, I believe, is also curved at the edges. So yeah, it's really difficult to make the algorithm work well for every shape people make. Like, you can make the weirdest shapes. And there's a whole bunch of kind of, let's say, things we try to do to make it better. For example, we find the largest square that you can fit into like the shape you made. And we use this square as kind of the center of the generation. So if you make like a T shape with like some weird like lines coming out of it, it's going to be mainly generated in the big square, and the T shape is going to be filled up later. So those are some of the things we do to kind of make it possible to generate rooms in weird shapes. But it's a challenge.
Hi, so you said you've used your algorithm in order to populate the room with furniture, but you're developing this for a tabletop where people are going to have their counters on and be moving their characters around. Did you have to add anything extra in to be able to account for pathfinding characters through the rooms, or did it just understand that from the layouts that you'd done originally?
Well, we have a system in place. Well, we don't really account for like actual, let's say, the thickness of a token or something moving through the room, but we do have a system in place that ensures that there's about a half grid tile of space. Like I call it a blocking grid, where it detects if you can move from the door to any other and reach any other object. With half a meter of room between them. So yeah, we do take that into account to make it as plausible as possible. Yeah.
When you process your straight skeleton algorithm for roofs, are you accounting for like height offsets for things like the windows? So if you have like a flat shape for the walls on the roof, and then the window sills that reach up higher than the actual wall heights. Were you able to reconcile that? And if so, how awful was that?
That's mostly an issue the 3D artists in our team are fixing right now. and some of them are in the room, so thanks for that. When you go to the second floor, we actually extend all the objects and all the walls and stuff to a bit higher, like to 2.6 meters, and we try to have all the windows fit into the raised wall so that they don't stick out. If they do, some of the really big windows do stick out, then it's kind of up to you if you really want to use a big window on a not so high building, then it's kind of up to you to deal with the consequences and like make it beautiful, I guess.
Hey, so
can you raise your hand if you're like speaking? Because I'm always kind of looking for. All right.
So back to the analysis. Don't you have the problem that you get a bit of overfitting with the examples that you give, or do you just have a lot of examples for it to choose? We learn from.
We have about 9 examples, so it's not a lot, but we try to make them as different as possible. So we have like 6,000 objects in Dungeon Alchemist already. So there's a lot to like decorate a bedroom with, and they're like every bedroom example has different closet and stuff. So we feel like we hit a good kind of trade-off between being consistent in making it look like a bedroom and generating enough variation. We also have a couple of other systems in place that I couldn't touch, like a variant system where like tables have variants where they like decked differently every time you spawn them. So sometimes there's like food on it, sometimes there's just plates, sometimes there's different food. That also makes everything more randomized and more like unique.
Hey, I was wondering if you've tried Paul Merrill's graph grammar for learning from minimal examples and doing this type of layout problem.
I'm sorry?
So there was a talk last year from Paul Merrill about graph grammar, and it seems like the perfect thing for this, where you can learn from a minimal set of examples and then do this type of layout. I was wondering if you've tried it.
I'm not familiar with it,
no
sorry.
worries.
So,
Hi, excellent talk. I have a question regarding your pattern-based approach. It's very nice to see old school stuff doing very well. I don't think you can actually describe all these semantic relationships between objects automatically with LLMs. Well, my question is about, you are applying these patterns, you're transforming lots of different levels that it can manifest in a myriad of ways. How do you test this? Is it correct by design because it's pattern-based and these patterns are correct, between quotes? Or do you also have test automation in place to identify potential problems in
well, we don't have test automation in place. Over the time, we wrote systems to automatically generate like 20 screenshots of like castle bedrooms, so we can like see if there was a regression in the quality of the bedroom generation. But we haven't actually used it yet. It's mostly just the whole team coming together and testing every different room and trying to figure it out. But usually, like once a room is tested and the analysis doesn't change, nothing changes in the generation. It's like it's just a random seed that changes. So, but honestly, like if there's one thing I would like to change in what we're doing right now is have more automated testing happening. But it's more a matter of lack of time than lack of will in this department.
Okay. Well, thank you very much for the lovely talk.
You're welcome.